In our fourth example, we want to find the first term in the sequence 6, 6 root 2, 12, 12 root 2, and so on and so forth, which exceeds 1400. So this is an infinite sequence. I'm told that because of this ellipsis. It continues forever, and my goal is to find out when I'm going to actually break through this 1400 mark. So this is growing. It's getting bigger and bigger and bigger, and at some point it's going to either equal or pass over 1400, and I guess I'm looking for when it goes over 1400. So I would say the probably the least complex but most time-consuming way would be to continue this sequence, counting and counting and counting until I get some number that's bigger than 1400. And we could do that. The next sequence would be 24, and the next term then would be 24 root 2, and then the next term would be 48. And I could do this for a while, and this would probably make a really long video, and I wouldn't get any views, and that's not what I'm about. So let's actually perform the standard operating procedure on this one and come up with the formula and use the formula to do the work for me. So to find the formula for this thing, I need to know what my initial term is, and I need to know what my common ratio is. And you can find that pretty apparently by looking at the sequence. So the first term is going to be the first term. So this is my u sub 1. That one's taken care of. So u sub n is going to equal 6 times. Now, as far as what my common ratio is, maybe you can see it right away, maybe you can't, but what we can do is we can take any two consecutive terms, and we can divide them. So let's divide, so the common ratio is going to equal 12 root 2 over 12, and the 12s will reduce, so this is going to equal the square root of 2. So since my common ratio equals the square root of 2, then I can use that in my formula. So this is going to be 12 times the square root of 2 to the n minus 1 power. So now that I know that, I want to know when this sequence is going to exceed. I want to know when it gets above 1400. So at this point, I suppose you could do some solving. You could set it equal to 1400, and you could solve for your n, and then take whatever the next n is, or we can use the graphing calculator to help us out here as well. So what I'm going to do is I'm going to take this as I'm going to take an approach using the graphing calculator, and I'm going to use the table function by coming up with a list of these terms in my sequence. So what I'll do is I'll go to the y equals page first, and I'm going to type in my sequence for the general term formula that I found. So 6 times the square root of 2, and that is raised to the hold on a second. Something got weird with these parentheses. Let me go back. So this is the square root of 2. There we go. And then that is raised to the n minus 1, or in this case, x minus 1 power. So this is my equation that will generate a list of terms. I'm going to go to my table. So I'm going to hit second and then table. And this is going to give me all of the terms in the sequence. And what's nice about this is since x is all natural numbers, I'm going to get actual terms. So I don't need to worry about things that would be in the equation but not in the sequence. So what I'll do is I'll just basically scroll until I hit a number that's higher than 1400, and it doesn't look like it takes that long. So once I get to between my 16th and 17th term, this is where I'm crossing over from before 1400 to after 1400. So I'm looking for the first term that exceeds it, and it looks like it's when my u sub n is u sub 17. That's 1536. So I'm going to write that down. So u sub 17 equals 1536, and this is all I'm looking for. This is the first term that exceeds 1400. That's it. So why don't you try this example? Do the same thing we did before. Use that graphing calculator to use the table function to find when the first term in this sequence exceeds 10,000. So give this one a shot. And it turns out that the first time that this sequence exceeds 10,000 is the 9th term. U sub 9 is equal to 13,122.